So just a very short lecture here, talking about differential equations in particular. Actually, our equations, this chapter, differential equations are so easy we don't even have to do what's called separation. They're going to be very, very easy. They're going to be like this first one here. So the idea is you have to understand that the solution of a differential equation is a function. If you want, you can think about it as a curve. So you're looking for a curve that satisfies some relationship between the function and some of its derivatives. And a lot of, you could nearly say all, probably a stretch, but the majority of laws of physics, which means engineering, are written in terms of differential equations. So for example, the beam equation expressing the relationship between the load on the beam, load per unit length, the Young's modulus, the second moment of area, the distance along the beam, and the deflection is given by a differential equation. So the differential equations that we're going to be looking at are actually going to be technically very, very easy. So for example here, this is the first derivative is equal to x squared. What you'll be able to do is anti-differentiate both sides. So if you anti-differentiate the first derivative, you get the original function y. The antiderivative of x squared is x cubed over 3. And then of course you pick up plus a constant, and you'll need some extra information to find out what that constant is. Now things get more difficult if you look at something like this, and indeed next semester we'll look at more difficult differential equations. We'll also later in this chapter, in this module anyway, look at differential equations where you can't actually anti-differentiate this. So there's kind of stuff like e to the minus x squared. You can't easily write down what the antiderivative is. Or maybe, say, for an applied example, you have the load per unit length not given as a formula, but in terms of data. So it's most laws in physics and engineering are differential equations. The order of a differential equation is the highest power. So this is the first derivative, so it's first order, second derivative, and then the one that you're going to be interested in later in this chapter is fourth order. And for us, usually if it's fourth order, there's going to be 4 anti-differentiations and so 4 constants. Okay. So we're also going to see these differential equations. This is a relationship between the shear and the load per unit length, the bending moment and the load per unit length, and the deflection and the bending moment. So a separable one, well, these, I really don't have to go into this, but if you do have something that's of this form, you can separate it, anti-differentiate both sides. But for us, all of them are going to be of this form, that the derivative or second derivative is given in terms of a function of x. And if you do separate and if you do anti-differentiate, you just end up with something. You could have just anti-differentiated both sides. The antiderivative of the first derivative is the original function, and then this is just writing the antiderivative f of x dx. So actually all we're going to have to do in this chapter is anti-differentiate both sides. As differential equations go, it's about as easy as things can get. Yeah, so that's just some theory. Now we're going to have to go into sections now where we talk about the different functions, new functions that arise.